morning, everyone. This is Sachin Fiske from Electrical Engineering Department, SND College of Engineering and Research Center. Today, we are going to start the zero hold system or sample hold system. In that, first one is the impulse sampling. Let us see if a continuous time signal x of t is sampled in a periodic manner. Mathematically, the sampled signal may be represented by x star of t is equals to summation of k equals to minus infinity to infinity x of t into del t minus kt is equals to x of t in summation of k equals to minus infinity to infinity del t minus kt. Let's consider this one is the equation number 1, or x star of t is equals to summation of k equals to minus infinity to infinity x of kt into del t minus kt. Here x star of t is the sampled version of the continuous time signal x of t, and low limits may be changed to k equals to 0 if x of t is equals to 0, where t is less than or equals to 0. Now, by taking the relationship between Z transform and Laplace transform, taking the Laplace transform of equation 2, that is x of s is equal to Laplace transform of x of t is equal to x of 0, and Laplace transform of del t plus x of t into Laplace transform of del t minus t plus 2x of 2t, and so on. So we get summation of k equals to 0 to infinity into x of kt into e to the power minus kts. Now we can define this e to the power ts is equals to z. So by taking in s domain as s is equals to 1 upon t in z, and x star of s is equals to summation of k is equals to 0 to infinity x of kt into z to the power minus k. This shows that how the z transform is related to the Laplace transform. The notation x of z does not signify x of s with s replaced by z, but rather x as s is equal to 1 by t ln z. Data hold. This data hold is basically a process of generating a continuous time signal h of t from a discrete time sequence x of kt. The signal h of t during the time interval kt is less than or equal to t is less than or equal to k plus 1 of t may be approximated by a polynomial in t as follows. So h of kt plus t is equals to a n t to the power n plus a n minus 1 t to the power n minus 1 plus a n t plus a 0, where the value of t is lies in between 0 to t, and it gives h of kt plus t is equals to a n t to the power n plus a n minus 1 to the power and so on. If the data hold circuit is an nth order polynomial extrapolator, it is called as nth order hold, and it uses the past n plus 1 discrete data x of k minus n into t. Now zero order hold. If n is equals to 0 in above equation, we have a zero order hold, so that h of kt plus t is equals to x of kt, where the value of t lies in between 0 to capital T, and k is equals to 0, 1, 2, 3. So h of t is equals to x of 0, and it is equals to summation of k equals to infinity x of kt into u of t minus kt minus u of t minus k plus 1 of t. And now by taking the Laplace of the above equation, we have h of s upon x of s is equal to 1 minus e to the power minus ts upon s. So what is the first order hold? Here h of kt plus t is equal to a1t plus x of kt, where the value of small t is lies in between 0 to t, where k is equals to 0, 1, 2, 3, so on. And now h of k minus 1 of t is equal to x of k minus 1 into t, so that h of k minus 1 of t is equals to minus a1 of t plus x of kt is equals to x of k minus 1 of t. So consider a unit step function input as h of s is equals to 1 minus e to the power minus ts into ts plus 1 upon ts square. The Laplace step transform of the unit step function thus gives us gh1 of s means h of s upon x of s is equals to, in first bracket, 1 minus e to the power minus ts upon s whole square into ts plus 1 upon capital T. Thus, obtaining the z transform of the function involving in the term 1 minus e to the power minus ts upon s. Suppose that the transfer function g of s allows the zero order whole as 0 of h into g of s. So x of s is equals to above equation, that is z transform of x of s is equals to 1 minus z to the power minus 1 into z in bracket g of s upon s. So reconstructing the original signal from the sample signal as defined omega s, where t is the sampling period, then if omega s is greater than 2 omega 1, where omega 1 is the highest frequency component present in the continuous time signal x of t, then the signal x of t can be reconstructed completely from the sampled signal x of t. Now, consider the frequency component omega 2 which falls in the overlap, and it has two components, and therefore the frequency spectrum of the sample signal at omega is equals to omega 2 includes the component not only at the frequency omega s but also at the frequency omega s minus omega 2, and this frequency is known as aliasing of omega 2. So what is aliasing? Two frequency x of t and y of t differ from each other by an integral multiplication of omega s. Sampling frequency at t is equal to 2 pi upon omega s. These two signals of the different frequency can have identical samples, means that we cannot distinguish between them from their sample. And if omega s is less than 2 omega, the original spectrum is contaminated, so x of t cannot be reconstructed. If omega s is greater than 2 omega 1, the original signal can be recovered by using an ideal low pass filter. The zeroth data hold does not approximate an ideal low pass filter very well, and higher order holds do a better job but are more complex and have more time delay, which reduces the stability margin. So zeroth data hold get used a lot. Thank you. Thank you.